In this post, I'd like to start decrypting deep learning. I'll do this by going through the steps in deep learning and show you that they're exactly the same as conventional machine learning, with some added benefits of using neural networks. We'll go through the same ML steps we did in our first post that was a simple ML problem, and show you how these steps apply to two common but very relevant deep learning applications. We will look at a computer vision problem and a natural language processing problem simultaneously. And while the two projects may seem very different, they have a lot of the same common steps as with any set of machine learning problems. We will keep our code analysis at a bird's eye view because we will be going in depth on these projects in the following posts. So we start off as usual with our first machine learning step, and that's the problem identification. And so for our first problem, our natural language processing problem, we'll be looking to classify toxic comments. So we have a data set that pertains comments, both clean and toxic, and we want to make sure we classify all the toxic comments. And there are other labels that exist in this data set as well, like severely toxic and identity hate, but we're not going to pay as much attention to them because we don't have as much data pertaining to those categories. So we'll focus on toxic versus clean. And for our computer vision problem, we're going to be classifying animal pictures. So we have a folder full of pictures of pandas, cats, and dogs, and we want to come up with a classifier to accurately recognize each animal. To develop these two deep learning pipelines, we're going to be using Python and Jupyter Notebooks. And for our text comment problem, we're going to be using the PyTorch and Lightning libraries. And for our computer vision problem, we're going to be using the Keras and TensorFlow set of libraries. Our second step in machine learning building is data collection. For the text comments, we got them from a Kaggle competition that they're part of. And for our cats, dogs, and pandas images, we had them on our local directory from a previous problem. One extra step in deep learning that is completely optional is data augmentation. In this step, you're increasing your dataset size through common deep learning methods. So for our NLP problem, our data augmentation step will consist of us translating our toxic comments from English to French and then back to English. And this ends up having the end effect where the word makeup of a sentence is different. There's synonyms being used, filler words end up being changed, things like prepositional phrases end up being changed. And for a computer vision problem, we'll increase the data size by taking images and applying a rotation and a random transpose. And this will have the effect of creating new images that look like they were taken of the same object but from different angles. Our third step in ML model building is data preparation. For deep learning problems, we're handling very large amounts of data, so our deep learning toolkit will provide us tools in the form of Python classes and methods for us to most efficiently handle our data. So for our natural language processing problem, PyTorch provides us with a dataset and data loader class for us to separate our data preparation activities from our model building activities. And we'll use the Lightning tools to effectively load our data, and it'll allow us to effectively load it in a lot of different environments. For instance, if we had environments that had a lot of GPUs or other resources. And for our computer vision problem, we use a Keras method to load our images from directory. Now that we have gone over our first 3 steps of deep learning, I'll show you the data collection, preparation, and optional augmentation step in practice in our Jupyter notebooks. I'll keep it at a high level since we'll be going over both of these projects in much deeper depth. For our NLP problem, in which we are using PyTorch and Lightning toolkits, since our data is just in CSV, we rely on the pandas read CSV method, just like our simple ML problem that we saw in our first post. For splitting up the data into the training, testing, and validation set, we rely on the train test split method from sklearn. We also had an optional data augmentation step in which we translated text from English to French and back to English. To handle the rest of our data preparation, we relied on the PyTorch dataset and data loader class to handle the activities before downstream model building. The PyTorch dataset specifies how our dataset is accessed and how individual machine learning observations are accessed. The data loader class specifies how our machine learning observations are loaded and gives us versatility in loading data, which is important when working with different computing resources with varying amounts of computing power. For our computer vision, we are using TensorFlow and Keras. We rely on the Keras method to read in our image data and also splits up the training and testing dataset. Keras also has a method for us to easily do data augmentation. Now that these steps are done, we can view a numeric representation of our data. Which is important because neural networks need numeric inputs for their data, and obviously images are not numbers. Our fourth step in machine learning model building is model selection. So for our text classification problem, we'll be using a simple linear neural network classifier, but we'll be using BERT as a tokenizer and training that alongside our linear neural network. And for our computer vision problem, we'll be using the 2D convolutional neural network that's the most common in classifying images. After model selection, we're ready for model training, hyperparameter tuning, and automated feature extraction. We train deep learning neural network models over the course of multiple epochs. We split up input data and feed it in by batches. We have to turn our input data into numeric format. These inputs are fed through different layers of the neural net in a forward pass. Our loss function informs the model on how well it's doing, and based on this loss, backpropagation recomputes the network's weights and biases. And our added benefit of doing deep learning is that the weights and biases that end up determining our feature are also optimized for this training problem. So, as we said, neural networks need numeric inputs, and obviously words and images are not numbers. So how do we get this data specifically into numeric format? For natural language processing problems, we use embeddings to represent text with numbers. And so we position text in a high dimensional space, and similar terms are closer together in distance. So here we see in a 3D space some terms being plotted, and we see that the similar terms are closer together. Our tokenizer, BERT, has been trained on a large amount of data and will provide us really rich contextualized embedding that understands a lot of different English language very well. Here we can see how BERT represents a simple phrase numerically. The phrase hello, world, ! is broken down into 6 different tokens, and each one of those tokens has 768 numeric values associated with it. So effectively that's 4,600 numeric values. And this very large array of numbers is what provides us with the rich context of language. And during fine-tuning of our model, we're going to be optimizing BERT's embeddings to understand whether or not a comment is toxic or not. In computer vision, we get a numeric representation of images by breaking down digital images into pixels. Each pixel has a color, and every color of the rainbow can be made by mixing or increasing the magnitude of 3 primary colors. Those colors are red, blue, and green. So yellow can be made by mixing red and green with no blue, and purple can be made by mixing blue and red without any green. While our image classification model is training, it applies convolution filters over the images. And after each training epoch, backpropagation will optimize those convolution layers for our given problem. And those convolution filters will determine our feature space. So if you want to know more about what a convolution is, you can check out this resource from 3 Blue, 1 Brown. And it is a pretty advanced topic for deep learning. If you want to think about convolution filters in a practical sense, you can kind of think of them like photo effect filters. An essential component of deep learning is backpropagation. Backpropagation is the way we do model optimization. We try to minimize a loss function, and this loss function provides us with a gradient to recompute weights and biases. So after each epoch, this loss function is computed, and it provides us with the data to recompute our neural network. For these examples, we're using cross-entropy loss, which is the difference between the predicted distribution by the model and the true distribution of labels. For our NLP problem, it'll be binary cross-entropy because we know a comment could either be toxic or clean. And for our animal classification problem, our computer vision problem, it'll be a sparse categorical cross-entropy loss function because we know our image could be either a dog, a cat, or a panda. When we are done fully training our neural network, we are ready to move on to our final step of machine learning building, which is model evaluation. Evaluation is done for deep learning in the same way it's done for conventional machine learning. In Kaggle competitions, evaluation is done by calculating the percentage of labels accurately predicted by the model. This is known as accuracy. Precision and recall. So precision in this case is the percentage of actual toxic comments out of what the model predicted as toxic. and recall, which is the number of instances that the model predicted as toxic out of all the actual toxic comments that exist in the evaluation sample. And for our computer vision problem, precision recall is those same type of metrics just for each individual class or animal. We also look at the area under the receiver operator characteristic curve, which is basically a plot of the true positive rate against the false positive rate. And we also look at the confusion matrix. Now that we've gone over all of our model building steps, I'll show you them for both problems in Python. With PyTorch and Lightning, we create our downstream model process using the Lightning module. This class defines what happens to the inputs in a forward pass and what loss function is used. We also customize what happens in our training, testing, validation, and prediction loop. We use it to log what happens at the end of our training epoch and what optimizer and learning rate scheduler we use. Once we specify our logging location and our training hyperparameters, the number of epochs, and the batch size, we are ready to start training. When starting the training, we get a message letting us know that some of BERT's weights are not loaded, which is fine since we are fine-tuning BERT's parameters for this problem. For our computer vision problem, we create our deep learning neural net model using the model class in Keras. We create the model using the functional API where we start from input, specify what happens in a forward pass, and finish with our outputs. When we call the model, we specify our loss, validation metrics, and what optimizer we use. And we use the .fit method to start training, just like PyTorch. We'll be going over the metrics that are produced while training, as well as the final model evaluation for both of our examples in the next part of the series. Thanks for tuning in.